let's start. So today we're going to talk about yet one more way to prove generalization bounds. So far we've discussed a bunch of different approaches to proving generalization bounds. We've done uniform convergence, we've done stability, we've done compression bounds, I guess a few more maybe. This is one more, and I will also have teach a lecture on online methods, probably, and that's yet another way to get to talk about generalization. The topic today is, in fact, broader than just generalization bounds. It connects to a variety of different subjects, such as differential privacy, adaptive data analysis. So, some of you in the audience might be more familiar with differential privacy than I am. Please stop me if you feel that I'm saying something wrong. I will mostly focus on various notions of information-theoretic stability and differential privacy as means of showing generalization. And we'll also talk about adaptive data analysis. I'm not going to talk about the various other aspects of differential privacy that are interesting in their own right. You can have a whole course on differential privacy. Okay, so the difference from what we've done so far is going to be that we're going to discuss a potentially randomized algorithms. Okay, so if you had before you had a f hat and that f hat sub n that depended on a data set S, right? This was our notation. S is the set of xy pairs from 1 to n. This was a function computed on the data. Now it's going to be a randomized algorithm, so this is a random output. Okay, so this is a random function. So there's one more random variable lurking, which is the internal randomization of the algorithm. So we're going to replace it with f hat n of s comma, and let's use one of the Greek squigglies like that. Okay, it's one. Should be close enough to one of the letters. Psi, I guess. In fact, because it's becoming so cumbersome, this notation, I will mostly just replace it with a single letter, W. So W is a random variable. As always the case, when you simplify the notation, you also hide a lot of stuff, right? So you'll have to decode it in your mind what it means, right? So W is actually a random variable that depends or jointly distributed with the data set, right? And you don't have to actually explicitly talk about this squiggly. You can just say that W is jointly distributed with the data set, right? So these are two random variables that are jointly distributed. And the range of W's as a random variable is the same as the range of the of f hat, right? So if f hat was taking values in the class of functions, then W is taking values in the class of functions, right? So it's a random variable with values in the class of functions. It's one of the functions that you could choose. In fact, lots of what we're going to say holds generically without even thinking about the class of functions. So you'll see in many examples, you can just think of this as analysis of random variables. Okay, so so once you have this, you have a conditional distribution. And we're going to denote it by P of, well, subscript W given a value of the data set, right? So given that you have this data set, this is the probability distribution over the hypothesis that you're going to generate, right? Everyone comfortable with that? So given S is equal to, I'm going to say little s. Okay, but little s is x1, y1, xn, yn. These are the realization of the data set, right? It's the capital S is the random data set. We can think of this as a particular realization of the data set. So this is the conditional distribution. Everyone is comfortable with that notion? So what is differential privacy? Let me just quickly jump into differential privacy. Differential privacy says that probability of W given S is equal to S. Now this is a probability distribution, right? So probability distribution, what's the input into the probability distribution? What's the argument? It's a set, right? It's a probability of some set. Let's call it A, right? A is a subset of the range of W's, right? And I'm assuming that everything is Borel measurable and so forth. Is no more than e to the power epsilon probability W conditioned on a different data set, S prime, A, plus some delta. And let me say it is a epsilon delta differential privacy. Epsilon and delta are two parameters, and this is a requirement for differential privacy, where this should hold for any measurable set A and any S and S prime. These are two data sets which differ in one element. Okay, S and S prime differ in one element. So the Hamming distance between these two sets, if you were to put things in the right coordinates, is 1, or at most 1. Okay? Any questions about this definition? Now, this on the surface has nothing to do with generalization or with anything that we've talked about, right? This is some property of the output of the algorithm, the behavior of the algorithm, as you change one data point in the data set, right? So what should happen is that the conditional probability distribution should not change too much, both multiplicatively and additively, when you change one point in the data set. And so this has a long history from like 2006 maybe, in explaining that if you have this property, then somehow you can't glean too much about any specific person, because whether the person was in the data set, let's say these are gene expression data of every person, whether this person was in the data set or was not in the data set, well, the probability distributions look kind of the same, so you can't really glean anything out of it, right? Or you cannot glean too much out of it. So are people familiar mostly with this notion of differential privacy? So who is not familiar? Oh, okay. Wow. Okay. Okay. All right. Right. So the original motivation for this is exactly what I was describing. How we make sure that an algorithm, a machine learning algorithm, let's say, that gets the data about all the individuals, does not really depend too strongly on any particular individual, so that you cannot get anything out of its output, right? So let's say you observe the output of the randomized algorithm, you shouldn't be able to say, this person is in that data set because that's the output of the random algorithm. But because the algorithm is random, if you ensure this, then there is some kind of protection against knowing or making conclusions about whether a particular person is in the data set. That's kind of the rough intuition. There's a whole field. There are books on differential privacy. I can defer to them if you want to read more. Right? It's a notion of a stability of an algorithm with respect to perturbation of the data, and the conclusion from that, if an algorithm is stable in this sense, is differentially private in this sense, is that you can't get too much out of the output of the algorithm. Okay, so let me not dwell too much on the issue of privacy, but let me just show you the connection to generalization. So the first connection is, let's write down the, I'm going to return to the original notation. Let's write down the expected loss or should I write it as, let me write it as expected loss, I'm going to write it out, of f hat when you train it on a data set S where the ith person, let's say, is replaced with a z prime. Okay? So that's that we understand. And now evaluate it. Let me write it as a comma z. Right, so this is a xy pair, and now you are asking, is f hat trained on this data, evaluated on the x, is that close to y? Right. Now I'm going to average it over only the psi variable. Okay. So this is everything is conditional on the data set, on the person that I swapped for the ith person, and the person on which I evaluate to test the output of the algorithm. Okay. Now, because of this property, I can swap the probability distribution. This is exactly the probability distribution of the psi, right? Because psi is my internal randomness. I can swap it to any other data set which differs in one element. So let me swap it to my original S. Okay. So this is upper bounded by e to the epsilon expected psi loss of, oh yeah, and I'm assuming that the loss is between 1 and 0. Right? Because when I'm swapping the measure here, the distribution, when I get the additive delta, that is going to multiply the loss, and then I'm just going to bound it by delta. Okay? So this is a f hat of S evaluated on Z, right? Because these two data sets have a different one element. Plus delta. So let me rearrange the terms. I'm going to subtract one guy. Okay, so I subtracted off one guy. Now this is bounded by 1 because the loss function is bounded by 1. Yeah? So this whole thing is bounded by e to the epsilon minus 1 plus delta. And this is roughly, let's say this is bounded by epsilon when epsilon is between 0 1/2, right? It's 1/2, then it's the square root of e. Let's see. So it goes like that. -1, it goes like that. Right, so I need to bound it by a linear function, so I just need to evaluate it at 1/2. I think that's right. Yep. So you see that this is essentially epsilon plus delta. Okay, epsilon plus delta. This is a very kind of back of the envelope calculation. But do you recognize this difference from last lecture? So this holds for any s, I, z, and z prime.
E to power epsilon is like the Taylor expansion 1 plus epsilon. So it should be greater than 1 plus epsilon.
Oh yeah, you're right. So let's do 2 epsilon, and let's make it up to 1. Yeah, because then it goes. Thank you. Then it goes at slope 1, and the exponential goes at slope. This goes at slope 2. The exponential goes at slope 1. Thank you. Okay, so 2 epsilon plus delta. Now, this difference holds for all data sets, all I, all z on which we evaluate, and all the z prime which we swap in. Does this remind you of anything? It's a uniform stability, right, from last lecture. Except we wrote it for a randomized algorithm, so we have to take expectation over this randomness of the algorithm. But essentially, it's a uniform stability. So differential privacy, epsilon delta differential privacy implies 2 epsilon plus delta uniform stability in this sense, right? So this is a very kind of back of the envelope calculation. So you see that differential privacy is a stricter, a stronger notion than uniform stability, and in particular it applies to randomized algorithms. Okay? Yes?
So what does epsilon mean over there? How did I get that to say?
This epsilon?
Yeah.
It's just controlling the multiplicative part, e to the epsilon. This is just controlling the multiplicative part. It's allowing the change in the distribution between 2 data sets to be both multiplicative and additive, and it's just that it's commonly parameterized as e to the power. This is a number greater than 1, rather than some other constant without the e. Questions? I think this thing was not turned on. Right. Other questions? Okay. All right. So this is a very strong notion, as you see, and it implies this version of uniform stability, which implies in turn generalization. Right? So you can already see how they're related, right? The notion of differential privacy and the notion of and generalizations. Right? No questions? So is this familiar to people or not really? Not really. Okay. I thought everyone knows about differential privacy, but maybe not. All right. Let's see. Let me see what's next. Okay, so let me go. Let me go to. Let me actually start from the end. Okay, let's start from the end. Let me give you a little bit of a history. So in the late 90s, early 2000s, there was this explosion of interest in stability. And in particular, this paper on uniform stability appeared in 2002 by Bousquet and LSA. That's the kernel ridge regression stability that we studied in the previous lecture. And then there was this huge interest in stability, lots of papers, and one could count probably around 15, 20 different notions of stability that was studied. It was a huge kind of zoo of different stability notions. One of these stability notions actually goes back to the 70s, 80s, and it was used for the study of k-means. K-nearest neighbors. That's your homework, by the way. For the homework, I stated another notion of stability, and I asked you to show and walk you through the steps to show that leave one out estimate, if you do k nearest neighbors, is a good estimate of the out of sample performance, which is not obvious because the k nearest neighbors effective function class is an infinite VC class. So for binary classification, you can see that you effectively are working with an infinite VC class, and yet you are able to prove a bound on the generalization gap, and that's due to this other way of proving things through stability rather than through trying to bound uniform convergence of means to expectations. Yes?
But in general, it seems like the local methods aren't going to be stable because, like, you add a single point to those, like, multiple things.
So local methods are k nearest neighbors, as you will show, is stable. K nearest neighbors is k over n stable, not in the uniform stability sense, but in a certain weaker sense. Yes. So you have to choose this, in which sense are they stable, and if you choose it correctly, then you can show the result. But again, there's this zoo of different stability notions, and for your favorite algorithm, it could be that this particular notion of stability is something you can handle, but not the other one. Right? Then somehow stability was almost forgotten, I want to say, after 2005. There was one important paper around 2010, and then it really exploded with differential privacy. So in differential privacy, which typically comes from computer science, people started studying sensitivity of the output to data like this, right? And in the context of not leaking anything about the data set. Then it was quickly realized that this also leads to bound on a generalization gap. Now, we already have, again, an explosion of different notions. I will show you maybe 5 of them and show you some relations between these 5 different notions of stability for the randomized algorithms. What's different about this time is that these are notions which are mostly information-theoretic. They're, or I should say, they talk about the distributions rather than the outputs themselves. So it's not that the output is the same, but the distribution of the output is the same, right? In this way, the distribution of the algorithm doesn't change too much upon the change of the data set. But the intuition and the motivation is very much the same as 20 years ago. Okay, so what I will do is I will give you a bunch of different notions and some relations between them without proof, essentially. Yes?
So why do you use to randomize algorithms for studying differential privacy?
So for differential privacy, you cannot do deterministic because you can always hide information when you talk about deterministic algorithms in your output, and then you can reconstruct it. So you can't talk about, well, not easily, about hiding stuff, right? Yes?
Maybe a related point is much like an adversarial game theory, you have these strategies and superior strategies. Likewise, here, there's an adversary or a path. That's why you might look at this strategy.
Yeah, so definitely you can think of this as trying to protect against an adversary, and one way to do it is by having a randomization, and not having a pure strategy. Okay, let me actually, so the notes are written in a slightly different way. I'm actually going to talk about adaptive data analysis first, and then I'll come back to stability. Okay? Is that okay? So remember that what we studied is this expected L of, now I'm going to call it W, right? Because it's the F hat of the data set, but now I'm just going to call it W, right? Minus the empirical of W, where this is under S, and it is the same S on which the W is evaluated and on which it was trained, right? So as we already discussed, the issue in bounding this is that W depends on S, and it's being evaluated on the same S, right? So you're trying to see whether the fit to data is a good proxy for out of sample, but there is a good degree of dependence. So let me now put it in a broader context of adaptive data analysis. So consider the following example. You're a statistician, or maybe you will be one day a statistician. You have your data set, S. Suppose it consists of a bunch of vectors. And you compute phi1 of S up to phi, let's say, m of S. Right? So you compute something. You compute a bunch of statistics. These could be empirical averages. They could be something else. Right? Now, phi1 through phi m are fixed functions. Just for the purpose of this discussion, suppose they're fixed. They're known to you. What are some of the examples? So suppose you do regression. You've got a bunch of coefficients in your regression, right? So suppose S is a matrix which is has rows as examples, columns are the features, right? So it's an N by D matrix. And now you do regression. This was X before, the X matrix. When you do regression, you get a vector of W or beta. If you're a statistician, it's probably beta hat. And now you've got a bunch of coefficients, and what a statistician would do is the statistician would say, hey, this is a big coefficient. That probably means that this variable is important. Maybe it's the, I'm going with an example in the paper of Russo and Zhu. Suppose these are your expression levels for different genes, right? These are the columns. And the output is a phenotype, so let's say height, and you want to know how the phenotype can be expressed. Let's say the height of the person can be expressed as a function of a linear function of gene expression for you, right? So you've got a regression, you fit the regression, and now you try to interpret these coefficients, right? So these could be m, in this case m is equal to d, m different coefficients that you compute from the data, right? So this is just to give you an example of what these are. These are statistics. A statistic is anything computed from the sample, including the coefficient of the regression, linear regression function, right? As long as this is something computed from the sample. Now, then the statistician would look at these outputs, and he or she would say, these are the largest ones, I'm going to pick them, right? Let's say the person picks the largest coefficient. Let W be that choice. W has values in, it's a random variable, and it has values in 1 through m. Right? Now, W could be a deterministic function of the phis. or it could be a randomized. Let's allow random choice in this procedure. So what is reported? What is reported is in the paper, right? Phi of sub W, well, of S, right? That's the one being reported. But you see W, the choice of W depended on the S itself. So it is an unbiased, it is a biased estimate of the actual quality of that gene in predicting the phenotype. You see the conundrum? And it is very much the same difficulty as using empirical value of your function as an estimate of the out of sample performance, right? Again, it's a biased Now, we do this all the time, especially if you're publishing in NIFS. What do? You have your data, you run a bunch of different algorithms, a bunch of different experiments, and then you pick the one that's the best, right? So of course a good practice is to keep fresh set of data. But who does that, right? I mean, you test you test the out of sample many times on this left out data set, right? And then report the best. What you really have to do is really never touch that test data, right? Never really touch. Only touch it once. So you wrote the whole paper, assuming that this is correct, and now you're 5 minutes before the submission deadline, you actually evaluate your model on the test set, and then cross your fingers, because if it's bad, then it's bad. Well, okay, but you don't want to, put roadblocks to science. You want to report the right thing, right? Now, of course, no one does this, right? So it's the same issue. So let me outline the issue. It's very much like this. You look at the expected value of phi sub W of S. And now you compare it to the expected value of, so what would be the unbiased version of this? Well, there is some mean. There is some unknown mean, Fi, which is the expected value of phi I of S when you draw different data sets S, right? It's an unknown mean. So what you are interested in is in this quantity, right? Now, is this small? Well, that's not clear, right? This is the bias. This is the bias of the procedure, of the selection procedure. So is the difficulty clear? This is very tricky. Right? If you use the data more than once, you can be in trouble, right? So here you're evaluating a bunch of things, and then you're reporting the one that was good. But it could have been good by chance, because these are random variables. If you're not accounting for that chance, you might discover something that's false. This is called false discovery rate, or the rate at which you're discovering things that are not there is called the false discovery rate. Right? So I'm just putting the question that we're studying in a broader context of adaptive data analysis. What can happen if you do if you look at data multiple times? Okay, so let me state the following lemma. not gonna cite people in this lecture. If it's recorded, I hope people are not offended. I'm just producing nuggets of truth. Okay. So if the loss function, oh, sorry, not the loss function. Let's call it if phi I minus the mu I are all sigma squared sub-Gaussian. In other words, that's a random variable that has tails that are dominated by the tails of the Gaussian random variables. Again, if it's bounded, you're fine. Yes?
Are the mu I fixed? And if they
The mu i's are fixed, yes. The mu i's are fixed. So here the expectation is over the W, right? That's a marginal distribution of the W. Right? In particular, let me say, that's a good question. So this should be well estimated by phi sub W of another data set. If you draw a fresh data set, and then you see, is my finding actually correct? Right? Is my finding actually good? Then that would be an unbiased estimate of this quantity, right? Does that make sense? Right. So you can think of this as, on average, you take another data set, a fresh data set, to check if what you found is good. Okay? It's like a test data set that you've never seen before.
So
Yes?
so changing the expectation.
Yes. So this is a, right. This is an expectation over W. Right, you're right. So it's like changing the expectations, right? Because this is the expectation over the data set S. Think of this as S prime, because it's a dummy variable. Then exchange the expectations. Okay, so suppose that they're sub-Gaussian. Then should I write down what it means to be sub-Gaussian more formally? We've never done this. So X is X with expected X equals to 0 is sigma squared sub-Gaussian. If expectation of e to the lambda x is upper bounded by e to the lambda squared over 2 sigma. Sorry, what is sigma squared? Sigma squared lambda squared over 2. I think that's correct. So because that's how what you would expect from a Gaussian random variable. Is that okay? You don't need to know this. Okay, so if these random variables are sigma sub-Gaussian, then the expected phi W of S minus the expected W of mu W is bounded by square root of 2 sigma squared, and then the mutual information between W and this vector of all the outputs, phi 1 of S, phi m of S. So Is everyone familiar with mutual information? Who is not familiar with mutual information? Okay. So I will define it in a second. Let's think of this as a measure of information that contained in the statistics phi. The amount of information contained in phi in the choice of W. Okay. Now I have to give an introduction to information theory.
What is the equation?
Mm-hmm. Yeah. So is everyone familiar with KL divergence? Yes. Okay. So it's just KL divergence between the product and the joint and the product. Okay, so let me maybe, it's a good time to do a refresher. Okay, so you have a random variable u and a random variable v. Actually, you know what? You don't even have that. You just have a distribution P and a distribution Q. It doesn't matter. Okay, so, you have a distribution P and Q. Everyone knows what the distribution is. And now you want to know how far is P from Q or Q from P. Okay? So let me just give you a bunch of possibilities. There is not a single possibility, just the way that you say 15 yards and I say 15 meters, right? Or, there are different notions of distances, okay? So one is KL divergence. So KL divergence between P and Q is just the expected log of dP over dQ. Okay? Now expectation is under P. The next one, so this is KL divergence. It's not symmetric. So d of PQ is not the same as Q and P. It's also called relative entropy. Relative entropy. Okay. So that's the first one. The second one is total variation. So let me denote it by little d TV between P. Okay, so here it's common to put comma Q because this one is symmetric. So this one is sup over a measurable set A of P of A minus Q of A. Guess if it's a sup. Okay, so supreme is taken over all measurable sets. Let me give you a few more. So this is total variation. Let's define max divergence between P and Q as a sup over A log P of A divided by P by Q of A. So this is a max divergence. Max divergence. Let's do one more. E gamma of P and Q is a sup over A. Again, it's not symmetric. Between P of A minus gamma Q of A. Okay, so this is called a E gamma divergence. Okay, you can come up with some other ones. Okay, the list goes on and on and on, and there are some relations between them, which some of them I will outline in a second. But the key is you fix some notion of distance between distributions. Okay, if you understand the first one only, or the first one and the second one, that's all I'm asking. Okay, total variation and KL divergence. Okay, so
is number 2 related to the Smirnov-Kolmogorov criterion? Statistics.
Yes, so if you put the empirical measure there, yes. Right. And you take the set of half raised. Okay, now take any one of these as a measure of distance, and it will give you a measure of dependence or independence between random variables. How? Well, if two random variables, let's say v, u and v, suppose they have a common distribution or joint distribution p, u, v. That's their joint distribution. So they're dependent. U and v are dependent random variables. Let's say your height and weight are dependent. And then there is a marginal u, and there is a marginal v. So think of this as a distribution of all people's heights. This is distribution of all people's weights. Right? So what has to happen for these random variables to be independent? Probability 101. It has to be product of marginals. The joint has to be a product of marginals, right? And that's the question, right? Is it or is it not? But you see, even little changes can make it dependent all of a sudden, even if it's not very important. So you want to quantify this. So you want to see how different is this from that. And we know how to measure distances between distribution. These are distances in quotes because they don't have necessarily the right properties, right? So from this you get d of p uv. Let's see if I wrote it like that. PUV and PU times PV. Well, this has a special symbol, and it's called mutual information. Okay, so this is mutual information. So this corresponds to the first one. You take the second one, and you get dTV between PUV and PU times PV. Again, this times means it's a product of these distributions, right? So this is called a total variation or just T information. Let's call it T information. T information. Okay, you get the idea, right? The third one, I'm not going to write it down, but you just plug in the PUV and then PU times PV, and then you get max information. So it would be called max information, and denoted by. So this would be the third one will be. So let's denote the second one by T UV. The third one is denoted by I infinity UV and called max information. And the E gamma version would be E gamma information. I don't know. You come up with your own. Okay? So again, to get a notion of dependence or independence, you first pick a notion of distance between random variables or distributions, and then plug in PUV and PU times PV. Okay, so now we can come back. So this result, so what this is saying is, imagine that the W, the choice of W, was made independently of the phi, right? So you're a statistician, you ran all these experiments, and then you picked one at random without looking, right? It's a dumb thing to do, but it would be the best thing to do, right? From this point of view. Because then the mutual information is 0, because PUV in that case is the same as P of U times P of V, right? Because you've made a choice independent of the output of your multiple analysis. Now this is 0, which says that indeed there is no bias, right? And it corresponds to our notion of if your algorithm output a function without looking at the data, yeah, then empirical is a good proxy for expected, right? This is exactly the same statement. Yes. The first one is over both, so it's a W and S as a joint. It's a joint distribution. So think of this as the result that you would report in your next paper, right? Like in expectation over the random data and my choice after looking at all these different things computed from the data, I pick the best one and I report it. That's a biased version of what you should have done, which is did everything and 1 minute before the deadline checked it on the fresh data. Okay? Make sense? Okay, so this is in the setting of adaptive data analysis. Now, let's go back to the setting of understanding the generalization gap. So let's look again at expected loss of your randomized algorithm minus the expected loss of the algorithm minus the empirical with respect to a set S of W, where the you're evaluating again on the same set on which you've computed the W. Yes.
I have a question over there.
Yes.
So we are computing the mutual information of W and phi. Are
which one?
So in mutual information over there.
Yes.
So you will say that I, W, and phi need to do the expectation of W in order to compute the information.
So this is saying what is the mutual information between the probability distribution of W and the probability distribution of phi. Look at the joint and look at the product of the marginals.
So,
And the measure of distance is exactly mutual information.
so that will depend on both S and W, or on depend on S.
Yeah, so you can think of phi as depending on S. Think of this as a deterministic function of S. Right. So it's just a transformation of your data.
W is also a function of S.
W is not just a function of S, it's a function of the phi, or it has a joint distribution with the phi, right? Because it's a randomized algorithm. So it looks at the statistician looks at all the outcomes and then deterministically or randomly chooses one of them. That's the W. Yes.
So this is very much a definite the worst thing is that mutual information through that uniform order and
Exactly.
just log of them. So it's like
Exactly. Actually, let me say this. So let me repeat what was just said. If you go deeper into the mutual information, you will see that it can be, at most, log the number. Log the number of values that W can take, because you can write it as a entropy of W minus the entropy of W given phi. And entropy is positive, so it's just the entropy of W, but the entropy can be at most log the number of them. So you get here log M. So what Sam said is that you recover our log cardinality result from, well, I mentioned it many times, right? If you've got a finite set, then maximum grows as a square root of sigma, 2 sigma squared times log the cardinality. Right? So this result nicely interpolates between independence when you get 0 and full dependence when you get log m. You see? So before we didn't have this ability to interpolate between these two. We had this notion that somehow algorithm depends on the data because it was computed from the data, and now it's being evaluated on the same data, so we have a problem, but we didn't get a hold of some notion of dependence. Like how do you talk about this dependence, right? This makes it more explicit. Okay? Questions? All right. So here you get, it's essentially the same result. So you get 2 sigma squared and then mutual information between W and the data set. Okay, so it's very much the same proof. Here you have a Markov chain data set. Now from data set you compute phi of the data set, and from phi you compute W. That's the choice, right? So if you know data processing inequality, you'll see that this is smaller than mutual information between W and S, because you've processed the data by computing all these statistics. Right? So I understand that maybe not everyone is familiar with the terms that I'm using. These are information-theoretic terms. Let me just, let this lecture serve as a kind of an introduction to the world out there where you can talk about random variables and how much information two random variables have in common. It's a very powerful notion which underlies much of communications and your computer, everything we have, cell phones and so forth. A notion of information. Okay, so here you have a simple bound. This holds if the function L of W, so little w, and Z is sigma squared sub-Gaussian. Okay, so you need this for any W to be sub-Gaussian. Okay, so now, yes?
So the right-hand side of this inequality and the lemma is data processing inequality, but the left-hand side, how they are connected?
Yeah, so the proof of this, the proof of both relies on a relatively simple lemma, which I will state in the notes. It's proved, but the proof is by, it's this big, it's not big, by Donsker-Varadhan duality of Kale. So you write out the variational representation for Kale. Okay, you don't have to know this. Okay, so at this point you can declare victory. You can say we've got a result on the bias of our algorithm, on the generalization gap, right? It's yet another bound on the generalization gap. And it has these nice notions that if W doesn't depend on S, you've got 0, which is exactly what you want. And if W is finite, then it's at most log cardinality, which recovers our result from 10 lectures ago. But the problem is that this is a bit of an unwieldy notion. How do you compute mutual information? So the rest is just getting other bounds on mutual information that are easier to deal with. Also, there is emphasis in the literature on differential privacy or adaptive data analysis on compositionality. So let me explain what I mean. Suppose you have a data set, S, and now you run an algorithm A. Let's call it A1. A1 is the first algorithm that did something with the data and produced an outcome. Now you take the algorithm 2, and again, as input, take the input of the previous. Maybe I shouldn't write it as S. Let me write it like this. So to this algorithm, you input both the data set and the result of the previous thing that you did with the data, right? Maybe you normalized the data and looked at it. Maybe you ran cubic splines and you looked at the output, right? So think of these as things you've done to the data. And now you have many things that you've done, right? So A3, again, looks at the output of all the previous results and the data, and so forth, right? So at any point, you know everything that happened so far. So this becomes a nightmare in terms of interdependencies. You know, I can give a whole lecture on how this can lead to false discoveries that are being published in the literature. As you know, there's this. You've probably heard of the controversy surrounding p-values and what does it mean to have this p-value? What if you do multiple tests and then you report this p-value? Do you have to divide it by the number of tests that you've done and so forth, right? Now this is even more complicated. You've done something, you looked at the output, you do something else, you look at the output, you do something else, and so forth. So there is a high degree of dependence now. Ideally, what you would like to say is that if every step here is limited in the amount of information that you glean from the data, then at the end of the day, this thing is small. Okay? So the empirical version is close to the what you want, to the expected version. Or in this situation, which is more general, right? Well, I don't want to say more general. Okay, let's say related. It's more general in one way and less general in another way. So again, you compute a bunch of statistics, maybe do it multiple times, and if each stage doesn't increase mutual information too much, then somehow this is going to be small, and then you have a guarantee that what you report is close to what you would expect if you really held out the fresh data set. Does that make sense? Should I repeat this? It was like 5 minutes, so I can't repeat it. But I can try again. Yes?
I don't understand like the multi-step part.
Yeah.
Does it, from my understanding, the case is like you have data and then you compute V and then you pick one from it and that's it? But
In this setup, yes.
yeah.
But suppose you did it multiple times. You looked at the same data again, and you looked at the output of the previous procedure. You ran something completely different. And then you did something else to the data. So you did a bunch of things that, let's say, get more and more information out of the data, right? So this dependence grows. Maybe not in this form, but the dependence between the output of the algorithm at the very end and the data grows more and more and more. And you would like this dependence, or this mutual information, to be smallish in order to guarantee validity.
But actually, I think what you do doesn't, it's not the point, just what you want to do is like keep the information to be, like, information to be small.
Yeah, so it's a tension. On the one hand, you want to get as much as you can from the data. On the other hand, if you get too much from the data, then you're chasing little things in your data that are not true in the general population. Right? So it's a way to prevent overfitting, or whatever that means. A way to prevent, a way to ensure that this quantity is small. This is well defined.
It is
Right.
like a version of bias and merits trade-off.
I guess so. You could. I don't know. I guess you could, like, if you had a parameter, let's say how many times you looked at the data, then maybe this quantity, or I can write it in this. There's a more general form of all of this that I haven't written down to avoid confusion. But right. So on the one hand, you want to do something smart with the data. On the other hand, you don't want to go after the little details of the data. So what I've presented is kind of an information-theoretic approach to this. Now, it's not clear that the different notions that you have here, I could work with all of them. It's not clear that they compose under this multiple look at the data, do something, right? But what I want to say is I want to say there are multiple stages, like these algorithms, and each one of them is epsilon delta differential private. How differentially private is my final output? So these are called composition theorems. Composition theorems. Many of these theorems are lemmas because they're not very difficult. Some of them are theorems. So they say that if you have this collection that you apply adaptively, I'm not going to write this whole thing out, but if these are the algorithms that you apply adaptively to the data, and each algorithm looks at the input from the previous stage and the data, and each of them is epsilon I, delta I, differentially private. Then composition is sum of epsilon I and sum of delta I up to m differentially private. So this is very nice, and this is not true for the deterministic notions of stability, such as uniform stability that we had before. So that's kind of where I think differential privacy and the information-theoretic notions of stability shine, because they compose. There are these composition theorems. It allows you to just control one stage, and that controls the whole composition. Okay. Okay, so again, the stress here would be on compositionality, as this is a useful tool for analysis. So in the remaining 10 minutes, what can I do? What makes sense to do? Well, is to give you a bunch of perhaps relations between the different notions of divergences, the distances between probability distributions, and relation to the differential privacy, and let me define one more or two more notions. So define erasure mutual information as I between W and S with a minus sign. Okay. And this is a sum of mutual information between the W and ZI conditionally on S with when you remove the I word. So the idea is we want to understand how our choice W, our randomized algorithm, depends on the data set, right? To understand it, perhaps what we could do is to see how our algorithm depends on each data point conditionally on the other data points. Okay? This is a notion of mutual information with a conditioning that I haven't described. I put down the definition in the notes. Essentially what you do is you just look at the mutual information as a KL divergence between these two random variables, conditionally on this random variable, but then you integrate over this random variable because this whole thing has to be just a number, right? So when you see conditioning, unlike the expected values where that makes the expected value random in what you conditioned on, here you have to integrate over what you condition on. Let me define erasure T information as T minus WS, same thing. T WZ S minus I. Okay. Where T information we defined before. Somewhere here, that's the information with respect to the total variation distance. Okay, so just a few nuggets of truth. If loss is bounded, 0 between the loss and between 1, then expected L of W minus L hat of W is upper bounded by. So this one is unnormalized, but it should be on the order of n because we're adding n terms. Each one is hopefully like epsilon, so it should be like n times epsilon. So this one is 1 over n times the distance between the, or the erasure information between W and S. Okay, so a few more results. Few more results. So first of all, I of W S is upper bounded by I minus W S. In particular, you could. This is when the data set consists of independent random variables, right? So I'm assuming that this is the I. I'm assuming that the random variable is independent of the rest of the data set. Right? Okay. If for any data set S and S prime differing in one example, so this is really like a stability notion. If KL divergence between PW S is equal to S and PW S is equal to S prime is less than epsilon, then I erasure WS is less than n epsilon. Okay, so how would you use this? This is like a forest of different notions. So I'm just showing you how to navigate in this forest, right? So imagine that you could show this stability. This is stability in the KL sense when you perturb one data point. Right? Very close to what we had for a differential privacy, except this is in the KL sense, right? Actually, you can write differential privacy in terms of the max KL, or max information. Okay, so if you have the stability, then erasure information is bounded by n epsilon. Now, erasure information, upper bounds, mutual information. Now you plug in mutual information. Did I forget n? I'm sorry. There's 1 over n here. Please fix that. There's n. So, because mutual information should be on the order of n. You have n data points. You're accumulating n times epsilon stuff, right? So this is one path. This implies that, implies this, implies that, and you're done, right? Just one path through this forest. Here's another path. If total variation between S is equal to S and PW S equal to S prime is less than epsilon, then erasure T information is bounded by n epsilon. Okay. Again, another path. If you're able to show this, put it here. That goes in here. Okay? You've got the result. Okay? So now you can say, well, you've showed us a bunch of abstract stuff, and you haven't shown us a single algorithm. So let me give you in the last 2 minutes an algorithm. Okay, so suppose W takes values in a class of functions f. So this is called a Gibbs algorithm. And we let L loss function be between 0 and 1, and let Q be a prior on F. So I'm assuming that you can put a probability distribution on F. I'm being Bayesian now. You will not see that often. There's nothing wrong with being Bayesian. W given S is equal to S. W is, so I'm going to put a measure to be proportional to the performance eta L hat with respect to the set S of W. Q dw. Right. So essentially I have a prior, and my data gives me the performance of every W in my class. W is a function. And I'm sampling according to e to the minus beta times the empirical performance of that function, right? This is called the Gibbs distribution. Okay? Okay, so for this algorithm, let me just state the result. For this algorithm, you can compute that KL divergence, this one, W given S is equal to S, and W given S is equal to S prime, is bounded by, can you guess? So S and S prime differ in one example. So you're sampling from this exponential distribution multiplied by some prior, but then this distribution changes a little bit by beta upon the change of one example. Right? So now you're sampling from this distribution. So how far is this distribution from this distribution in KL divergence? Anyone wants to guess? Just a rough order. Yes.
What is beta?
Oh, beta is temperature. Sorry. So beta is just some temperature parameter.
What is the distribution?
Oh, in this term. Just a parameter. The parameter of your Gibbs. It's a number.
Oh, so this is what the algorithm.
Yeah, I'm defining an algorithm. This is the Gibbs algorithm with a parameter beta. It's also a stationary distribution of a random walk with an appropriately scaled additive noise. I think Tommy will talk about that. So, can anyone guess at least the order? What is this KL divergence bounded by? Come on, just guess something. 1 over beta? Beta is actually upstairs. Okay, so beta squared divided by 2n squared. That's the result. Okay, let's quickly get the generalization bound for a Gibbs algorithm. You take this, you put it in here. Epsilon here is now beta squared over 2n squared. it implies erasure information n times epsilon. This goes here, n cancels, and you get beta over n. So the generalization gap expected L of W minus L, L hat of W is bounded by some small constant times beta over n. I think the constant is 1/2. Yes. Beta over 2n. Okay? Yes?
What happened? Sorry, what happened to the sigma number?
Yeah, good. So L is between 0 and 1. Any bounded random variable has a finite sigma, and for 0, 1, it's actually a quarter. So that's the sub-Gaussian parameter. So 1/4, you plug in 1/4, you're done. Right? Was that easy? That was pretty easy. So the point is that you when you sample in this way, you don't go with the empirical, but you randomize around the empirical, right? You randomize around the best empirical value. Then you gain in the stability, mutual information stability. Okay? All right. We'll see you on Wednesday, and Tommy will speak on Wednesday about approximation theory.